All right, my name is Andy Schweitzer, and this is a short video on the properties of covalent compounds. This video will basically encompass three things. One, what is a molecule? How will that compare to a bulk crystal like of an ionic compound? How do we go about dissolving molecules, and then melting points of molecules? All right, so a molecule versus a bulk crystal. A few things, again, I'll review here is that an ionic compound is just purely a pile of cations and anions. I'm going to change my color here. So cations, anions, cation, anion, and it's depending on the actual molecule, or I should say the ionic substance, would be determining on whether or not. Apparently I can't talk and draw this out at the same time. So here we go. All right, so this is our ionic crystal. Okay, I have one cation for every one anion, but depending on the ionic substance, you may not have that ratio. It could be 3 cations for every 1 anion, and then of course it would follow along a slightly different pattern. Either way, the cations and anions will attract. Cations themselves will repel other cations. Negative anions will repel other negative anions, and they'll form a sort of give the opportunity a bit of a pattern. Now, of course, I split that in half. I still have cations and anions on one side, cations and anions on the other. And of course, we would call this little ratio here its empirical formula. We don't know how many we have, so we just take the simplest ratio of atoms. Now, a molecule, let's say, for example, water, okay, this is a self-sustaining little group. It's covalently bound. In this case, it's 2 single bonds. The exact number of atoms in here is exactly specific. I cannot cut this in half. It forms a very much different phenomenon than this guy. Let's say, for example, C6H12O6. Now, this is an organic compound. It is a molecule of glucose. So this guy has a common name of water, H2O. This guy has a name, well, it'd be water. And this guy has a common name would be glucose. So we won't be dealing with, we have already dealt with a bunch of these bigger organic compounds, but in this chapter we'll be dealing with simpler inorganic covalently bound chemicals. But in some sense I like this chemical because it shows that all these particles are necessary to form this substance. In fact, it's a carbon ring that can be a ring. It actually goes from a ring to a straight and then goes back and forth. But either way, this molecule of carbons that are inside of it, a little ring, and it forms a very specific little unit. I can't cut it in half to make half the carbons on one side and the other. I can't break it in half. It will no longer be glucose. There's exact number of atoms, and for that reason, we'll use a formula to give the exact number of atoms, and that would be, it's called the molecular formula. Sometimes they will use molecular formula where maybe they shouldn't, as far as naming is concerned, but in this case, the definition of this guy is simply the exact quantity of atoms that are in a molecule. Okay. But again, if I have a great big pile of ice, of water molecules, that means I just have a whole bunch of these molecules that are just simply stacked up on top of each other. And they can form nice little snowflakes or whatnot, but each of them are their own separate entity, and they would create a little pile of water molecules. Very different phenomenon versus salt. I could break this in half, and of course it's going to form a jaggedy little line here. It's not going to form a straight line like it would along these, but again, You got to understand how it looks on a molecular level. All right, dissolving of molecules. So we saw how ionic compounds dissolved in the last video, but in this case, we do know that some molecules will dissolve. And some will dissolve in polar substances, solvents, some will dissolve in non-polar substances, just depending on the actual chemical. But in some sense, once again, why do things dissolve? There has to be some attraction between the solute. Let's say the stuff here is the solvent, and I'm going to dissolve into this thing some All right, so we have this solvent here. I'm going to call this the solvent, and I'll be dropping stuff in. I'm going to say these little circles are the solute. So if you're making Kool-Aid, this would be your water, and this would be your solute. So now for the solvent of water, of course, water is polar, and it has hydrogen, oxygen, hydrogen, and it's got a region here that's positive, a region here that's negative. So why would something dissolve in here? Well, let's see how this goes. We got our like this. Okay, so this region being relatively positive, this region being relatively negative. If this thing also, the solute also has regions of positive and negative, it also can dissolve. And we haven't discussed a whole lot about this yet, but if we look at a closer view of this solute particle, it is actually possible for maybe part of this thing to be slightly negative, and therefore their side is slightly positive. And then when this thing goes into solution, it would possibly orient itself in a solution in a way that maybe the negatives would be huddled around this side and the positives would be over here, and maybe over here would just rotate around, and maybe the positives would be on this side and the negatives would be over here. So there is some sort of attractive force inside this particular solvent solute attraction, and of course that attraction would be equal to Coulomb's law, charge not of a cation but of something positive and then something negative, and then there's a distance between those charges. So those would eventually have to fight off the gravity of forces pulling it to the ground. But if there is no attraction between the solute and the solvent, yes, gravity pulls to the bottom. Otherwise, there is always going to be some likeness that could attract here to bring it down. We will be talking more about this particular idea of a substance having little side charges. This is called a polar molecule, and that's our next topic, which we'll be discussing. I did use the word polar in describing the solvent as well, a polar solvent. All right, melting points of molecular solids. Now, when I take an ionic compound, and of course I have a cation, and I have an anion, and these guys are really attracting to one another. It's a very strong bond, and that is why almost all ionic compounds, and of course you'd have an anion right here, and maybe another cation here, and they're attracting here, and they're attracting here. Ionic compounds have very strong bonds, and they are almost always solid, and that's solid due to the fact that they have these very strong attractions between the molecules. These aren't covalent bonds, they're just lines showing lines of attraction. Therefore, this attraction is making it solid. When I melt this particular substance, okay, when you melt an ionic compound, you're actually breaking an ionic bond. Now let's look and see how that might be different for a covalent compound. Let's just say, for example, two compounds. It could even be A, and A might even be able to attract to another A to form a solid A. Now, if there is some amount of attraction between these two particles, okay, it's not going to be a covalent bond, but if you have some amount of attraction, there is a possibility they will stick together and form a solid. If there is maybe even a small amount of attraction, then maybe they will just form a liquid. And if there's almost no attraction between these two things, well then we're going to have essentially a gas. But in some sense, you have to be aware of that there are bonds inside of A which are covalent. And this is what we refer to as an intramolecular bond. Okay? And all the stuff that's between the two particles we call intermolecular. Okay? Now, so when you melt a solid, when you melt an ionic, or I should say covalent compound, you are not breaking a covalent bond. You're breaking these weak intermolecular forces. Okay? Now, because they're weaker, they're considerably weaker than, let's say, an ionic bond. That means that covalent compounds can be present in all three of these phases, on Earth at least, like solids, liquids, and gases. This is a small curly QL. Either way, so we warm them, and we have to simply shake these atoms so that they can separate from each other, and it's just not that hard to separate them because the attractions are very weak. There are a few different types of intermolecular forces, and the most common one is called, we call it IMFs, intermolecular forces, and hydrogen bonding is probably the most common one. See a lot in biology. Another form of this, I call another form, is it's called a dipole. And the last but not least, we have what's called London forces. This video is not going to really discuss that much about any of these intermolecular forces. You should just be aware of that they are present between covalent compounds. And if you have something that is maybe a solid, then you would expect that they have more of these forces gripping these atoms and bringing them together. Easily you could have, H2O as a solid. That's definitely lots of hydrogen bonding, for that matter, holding it together. But let's just say, for example, oxygen. Looks like this. Is there anything really taking one oxygen molecule and attracting it to another oxygen molecule? Even if you don't know much about these intermolecular forces, or anything about IMFs or anything of this nature, you should be aware that in real life, these two don't stick together. So there's really not a whole lot of intermolecular forces between these two substances. Therefore, more likely to be a gas as opposed to a solid. That ends our talk on covalent properties.